Should we get started? Okay, everyone. Okay, great. All right, hi everyone. Welcome back to the AMD online seminar series. We are happy to have you with us. We are also delighted to have Professor David Parks with us as our distinguished speaker. David is the George Clooney Professor of Computer Science in the Paulson School of Engineering and Applied Sciences at Harvard University. He's the co-faculty director of the Harvard Data Science Initiative and co-chair of Harvard Business Analytics program. David received his PhD from University of Pennsylvania, and his research focuses on AI and economics. He founded the Harvard's EconCS research program that we all know is very successful. And for all his numerous contributions, he received several awards and recognitions, including being a fellow of the ACM and AAAI, and being a recipient of ACM SIG AI Autonomous Agent Research Award, the NSF Career Award, Alfred Sloan Fellowship, and Thoron Scholarship, as well as Harvard's Rosalind Abramson Award for Teaching. Today, David is going to tell us about differentiable economics. David, we are very happy to have you with us. Thank you for joining us today, and the floor is yours.
Well, thank you. Thank you for the chance to share what we've been working on with this audience. I'm really happy to be here. This is a talk about this topic of differentiable economics that we've been working on for a few years now, which we think is providing a new and interesting way to think about how to use the tools of machine learning to do economics in a new way. Let me start by sharing with you this overview of the inverse problems that people work on in economics. Of course, there are many. I'm sure many of you are familiar with optimal auction design as a challenge problem, but also design of matching markets or congestion pricing or contract design. When we say these are inverse problems, what we mean is we mean to contrast the forward direction, which is I design an economic system and that induces an equilibrium and in turn an outcome, with the inverse problem, where we're interested in a particular outcome in the economic system, and we have to go in the other direction through the equilibrium to try to think about the design of the rules. So these are inverse problems because we need to go backwards through the equilibrium. And the typical recipe for solving these, I think you can very easily see in Meyerson's work from the 1980s, where Meyerson, of course, was thinking about revenue optimal auction design. So Meyerson says, okay, I'm interested in finding an allocation rule, a payment rule, and I'm looking to solve a problem where the thing I'm optimizing over are these functions, and I'm looking, in his case, to maximize the expected revenue. So I have a distribution here over the valuation profiles, and this is the total payment I collect. I need feasibility of my allocation rule. I need individual rationality, meaning I need each agent to have non-negative expected utility. And then I need incentive compatibility. I need agent utility from providing a true report to be weakly larger from reporting any misreport. Now, the typical way this thing goes for solving problems like this is that you find a characterization result, and through the characterization results, in Meyerson's case, he shows that you can use monotonicity. Once you have monotonicity, you can use virtual valuations. You formulate an unconstrained optimization problem, and you can, in his case, analytically solve that problem. But as we know, these problems generally are very challenging. And in fact, even the two-item generalization of the optimal auction problem is not completely understood even 40 years after Meyerson's paper. Just so you can see before we get into the main talk, so you can see how things get interesting. even for a revenue optimization problem with a single bidder, when I'm selling two additive items whose values are distributed uniform 0, 1, even in that case, the optimal allocation rule is surprisingly intricate. This is showing as a function of the value of agent 1, of the value of the agent for item 1 and the value of the agent for item 2, the allocation space. Over here, it gets items 1 and 2. Over here, just item 2. Over here, just item 1. And you can see there's already a combinatorial type of structure to the allocation problem, even though this is a very simple revenue optimization problem. Okay. So then you might ask, well, is there a role for computation in trying to solve these inverse problems? And this traces back to the work by Konitzer and Sandholm from 2002, when they coined this idea of automated mechanism design, where they said, okay, well, at least for a setting where the types are finite, we can, rather than working with the functions directly, we can represent those functions on the grid implied by the type profiles. So imagine having a decision variable for every possible type profile and kind of representing your allocation rule that way. And a decision variable for every possible type profile that represents the amount you will charge to each of your agents. And if you can write down that big optimization problem, which you can write down as a linear program, you can impose the incentive constraints and other kinds of constraints, and you can hope to solve it. Now, the problem you can immediately see with this formulation is that the number of variables and the number of constraints will grow exponentially in the number of agents. So if little d here is the size of the type space of any one agent, I've got very quickly a very large linear programming formulation of the problem. Fairly soon after that, the work wasn't published until a few years later, but fairly soon after that, people started to also think about solving constrained versions of this. So what if I have a parametric space of mechanisms? Maybe I can try to search through that parametric space. This makes it more feasible, but it also is restrictive because obviously you're restricting your solutions to the space that you're searching over. And more recently still, there's been quite a lot of work in the computer science community on the Bayesian version of this. So this is the Bayesian algorithmic mechanism design problem, where relative to the early 2000s work, where we were looking for strategy proofness, for dominant strategy incentive compatibility, this is Bayesian incentive compatibility. The advantage of Bayesian incentive compatibility from a computational perspective is that you can work in the interim space. You can represent the allocation rules, if you will, in expectation over what the rest of the system will do. That avoids the exponential representation cost. But in return, you're getting Bayesian IC rather than dominant strategy IC. And so the gap that is left here is we don't have scalable methods for optimal dominant strategy incentive compatible design. And also, a number of the problems I started my talk with, if you think about problems of contract design, as an example, or problems of tax policy design, these are not direct revelation problems. These are indirect design problems where you design the incentives, the rules, the affordances, and that induces a behavior on the system. And there's no meaningful sense of imposing incentive compatibility on those design problems. So these techniques are not addressing that problem either. So what we've been working on since around 2017 now is this idea of trying to model the rules of an economic system through a flexible differentiable representation, through a neural network. So the idea is that the neural network itself will represent the functions that are the object of our design. So the neural network will literally represent, in the case of an auction, a mapping from bids into allocation and payments. Or in the case of a matching mechanism, a mapping from reported preferences into a matching between the two sides of the market. This is using technology like neural networks as nonlinear function approximations. Notice you don't need to discretize the space. And the hope is that by setting up these inverse problems this way, we can appeal to the toolbox of machine learning, methods like SGD as a way to optimize, and then use those tools to solve these inverse design problems. The key challenge, of course, is that when we think about the inverse problem is all about the incentives or the implied equilibrium of the rule that you design. And so the key challenge is to bring that essence of the inverse problem into the machine learning pipeline. You can think about it that way. And I'm going to explain this in today's talk in 3 different settings. I want to try to give you an overview of some of the work that we've been doing. One setting will be revenue optimal auction design. The second setting will be two-sided matching design. And the third setting will be a particular example of indirect mechanism design, in particular for sequential pricing mechanisms. I'll explain what they are when we get to that part of my talk.
David,
yes.
Sorry to interrupt. I think there is a question by Rika. Rika, feel free to ask the question. Okay, so
it was mistakenly raised.
Okay, all right. Sorry.
Okay, great. So let's get into the first section. This is talking about revenue optimal auction design, and this is work that we published in the ICML conference in 2019, and it's work with Paul Duting, Zhi Feng, Hari Narasimhan, and Sai Srivatsa Ravindranath. The setting that I'm going to describe, just to illustrate this, imagines a seller with M distinct indivisible items, a set of N additive buyers with valuations expressed through V sub I1 through V sub I M. This is the value of buyer I for each of the M items. We're assuming access to a distribution on the buyer's valuation. And we're looking to design a parameterized auction. So this G sup W, T sup W is denoting that the allocation rule and the payment rule now will be parameterized through the parameters W in a neural network. And we're looking to find these parameterized rules that maximize the expected revenue implied by those rules, subject to dominant strategy incentive compatibility. And just as a reminder, or to make sure we're all in the same place, just remember that what we mean by dominant strategy IC is that the utility to bidder I is larger than its utility it could get for any misreport V hat I. And this should be true for all bidders, all valuations of that bidder, all misreports, and all valuations of the other bidders. And I'll be using strategy proofness interchangeably with DSIC. We've been working with a number of different architectures in this work, but let me describe 2 of those architectures to you. The first architecture we call RocheNet. That points back to an earlier characterization theorem provided by Roche, which influenced the design of this network. This is a neural network architecture that provides a dominant strategy, incentive-compatible auction for a single bidder. So this architecture will be restricted to maximizing expected revenue when selling M items to a single bidder, where you know the distribution over that bidder's valuation. And the idea in this architecture is very simple. The idea is to, so here's the input. This is representing the additive bid of the bidder. Here's the output. The output in this network is actually going to represent the utility that a bidder with valuation B would receive according to the rules of the mechanism. And we'll think about each of these units in the hidden layer. This network only has one hidden layer. We'll think about each of these units in the hidden layer as representing a choice available to the buyer. So each of these units, for example, H sub J, is doing a very simple calculation. It's taking the inner product between what we can think about as the randomized allocation associated with that unit. So alpha sub J here is a 0, 1 vector of M dimensions that represents the allocation to the bidder associated with that menu item. So then the inner product between that and the bids of the input represents the expected value of the bidder. And then the other parameter associated with a hidden unit is beta sub J, which is the payment associated with that menu choice. So in other words, what I'm representing through these H's here and through the parameters associated with them is nothing more than a menu set. It's a set of choices of randomized allocations and associated payments. And then by including a maximization unit here, we insist that for a bidder that provides its true valuation, that the network will implicitly select on behalf of that bidder the choice that maximizes the bidder's utility given that reported valuation. Max is not differentiable, but when we train, we replace the max with a soft max. And then essentially the loss function that we use in the training loop, and we're used to minimizing expected loss when we solve a machine learning training problem. The loss function is the negated expected revenue implied by the distribution over types and the choice made through the network architecture on behalf of the bidder. Okay, so it's a single hidden layer. It has this additional softmax at the output layer. This is now well defined, and now we can appeal to the machinery from training neural networks to go ahead and train up Roche nets for different economic contexts. And in particular, we can change the distribution of the inputs. And as we change the distribution of the inputs, the hope is that the network will provide optimal solutions to that economic design problem.
David, quick question.
Yep.
Earlier, when you talked about the existing literature, you mentioned the work by Manelli and others, and you had this diagram from their work with 2 items. So in that setting, I can see how, in which regions the payoff of the agent may look like what. Is there a way of, systematically thinking about what type of utility structures can be presented using the architecture in this slide?
Sure. So you can think about each one of these as representing a different part of that allocation space. Actually, let's talk about that right now.
Oh, okay.
So here's the allocation rule that is associated with their optimal design. Let me actually show that by decomposing it to the implied probability of allocating item 1 and the implied probability of allocating item 2. So this is the same rule. I'm just now decomposing it, and I'm showing you that if your valuation is in this space, then you will get item 1. if your valuation is in this space, you will get item 2. And Ozan, the way to think about this is that this is a menu choice. This is a menu choice where I will give you both items and I will charge you a particular amount. This is a different menu choice. This is a different menu choice. And now we can look at what happens when we train RocheNet on this problem. And in this case, we set up the network, we give it 100 units. So it can, in principle, select as many as 100 menu items. And when we train the network, this is the results of training. So I've shown you now through a density plot the results of training the network. And the network is able to essentially exactly recover the shape of the RocheNet design. And we can do the same thing for other results in the auction theory literature. This is a paper by Pavlov from 2011, where there's one bidder, the 2 items now have unit demands. It's straightforward to modify the Roche network architecture to handle unit demands rather than additive valuations. Now in the Pavlov problem, the values are uniformly distributed on 2, 3, and you can see again, this is the allocation rule of the optimal design. And you can again see what happens when we train RocheNet. And again, RocheNet is able to essentially exactly recover the design of the theoretically optimal auction. And the nice thing here is that we haven't had to discretize the space to solve this. We're just directly appealing to the continuous parametric representation provided by the neural network. Yep.
David, one question from Peter Crampton. Peter, you want to ask the question? Okay, yeah, I think I can also. You should be able to. Yeah.
Yes, David, good. This is wonderful. Quick question. In many auction design settings, we're more interested in efficiency rather than revenues because of repeated interaction, or the designer cares about both sides of the market. I assume your methodology would apply, but the analysis would just be simpler. Is that correct? Or do you have any thoughts about efficiency rather than revenues?
Yeah, there's absolutely no problem with efficiency rather than revenue. Really, nothing changes. You can also, if you want to do max min type things, you can do that as well, Peter. It's very flexible. Basically, I would think most practically relevant functional forms could be represented within the loss function.
Excellent.
Yeah. That was for the architecture we call RocheNet. RocheNet is for a single bidder. Of course, we're typically interested in multiple bidders when we're doing auction design. So the second network that we've been working with, we call RegretNet. RegretNet, again, is an extremely simple idea. The idea in RegretNet is to have a neural network. In this case, we use a neural network with 2 hidden layers. Each hidden layer has 100 units. That represents the allocation rule. And then we have another component of the same neural network that represents the payment rule. Let me explain the allocation component first. So this is a setting with m items, n additive bidders. Each of the bidders has a bid ij for item j. So again, here are the inputs. This is the input from bidder 1 all the way through bidder n. These are my hidden layers. In this case, these are tanh activation units, but they could be other nonlinear activation units. We don't think it's especially important which ones you use. And then what we have on the output layer of the allocation network is we have these softmax groups. So this softmax group insists that these z's are a well-defined probability distribution over the allocation of item 1. And that repeats in the output layer all the way down to this being a well-defined allocation distribution over item M. Right? So this is my allocation network. Notice that because we want these things to be differentiable, we do have randomized allocations. So at the end of this, I have randomized allocation. Then the payment network, you should think about this all as being part of the same larger neural network, but I'm showing you two different components of the network. We train them both at the same time. The same idea, you have two hidden layers. And now at the output layer, I have one sigmoid unit, which is just making sure that I have a output on 0, 1. And then I would think about alpha sub 1 as representing the fraction of the bid value of the bidder for the allocation it receives that I will charge it. And so if you want to think about the entire network, this alpha would be multiplied with the expected value implied by the allocation part of the network. And those two things together will give the expected payment that we would charge of the bidder. And by setting things up this way, by making sure that the payment is a fraction of the value, we get individual rationality for free through the architecture of the network. The thing that I haven't explained to you yet, which you get for free with RocherNet, but you absolutely do not get for free here, is I haven't explained to you yet how we can achieve incentive compatibility. So far, if I just trained this network to maximize expected revenue, it would learn to set the price, it would learn to be efficient and to extract all of the value from the bidders, which would not be incentive compatible. So how can we achieve incentive compatibility? The first thing that we observe is that, okay, so here's my loss function. This is the same type of thing you've seen before. You can read this as going all the way back to the Bayesian formulation, if you like, except here I don't need to multiply by the payment, because this is just the expected payment for a given type profile. I'm reformulating strategy proofness in a way that is equivalent up to 0 measure events, but lets me work with an expectation. I don't want to have to write down for every type profile because I've got a continuum over type profiles. So I want to work with expectations instead. So what you can recognize is that if you define regret to be the maximum utility gain to bidder I from a misreport at a given profile V, this is the typical notion of regret. I might sometimes refer to it as ex post regret. This is the amount you could do better once you know the reports of everybody else. Then this is nothing more than the expected ex post regret. And if this is 0, notice regret is always non-negative, then if this is 0, it means the regret is 0 everywhere except for 0 measured type profiles. And if the regret is 0 everywhere, this is equivalent to strategy proofness. So this is the first thing that we do to try to handle incentive compatibility. But it still leaves the question, okay, how can you handle constraints when you're using a SGD style approach to train a neural network to solve an optimization problem? What we do in this work is we use a Lagrangian method. We actually use an augmented Lagrangian method, so there are actually quadratic penalty terms as well. I'm not going to show you those terms here, but here's the typical Lagrangian term you would expect to see. I'm going to expand on this on the next slide. Just before I do that, let me underscore one thing that sometimes is not clear to people. There's no training labels in this problem. This is not a supervised learning problem. I don't need Roger Myerson or Peter Crampton to tell me what to do profile by profile. Rather, I use the machinery of machine learning by defining a loss function. And the loss function is capturing the idea that I care about revenue, but I want this to be strategy proof. Okay, so here's my Lagrangian problem. And there's a challenge in solving this, which is there's something that I've hidden, which is that this regret has an inner maximization problem. Because regret is about finding the best defeating misreport. The misreport V hat I that is best for the bidder, you can think about as defeating the intent of the designer. And the question is, how am I going to get at this? Because at the moment, this doesn't look differentiable. And I need to be able to take the derivative of regret with regard to the parameters of the mechanism. But I have this maximization in that regret function. Notice, though, that if I was able to find that optimally defeating misreport, then this is just a linear function, and this becomes differentiable. And so the key challenge which we need to solve within our learning loop is think about a sample evaluation profile, and then for a given valuation profile, to be able to calculate the derivative of my objective with regard to the parameters of my network on that profile, I need to first of all try to find these defeating misreports. I will then fix them, and then with those pinned down, take the derivative. And the way we do that is we adopt an adversarial style. This is a phrase from the machine learning community, where the intent here is that we do gradient ascent on the input to the network to try to find a defeating misreport. Okay, so what do I mean? You fix the parameters of the network, you fix the inputs of everybody but a particular bidder, and you try to follow a utility improving gradient for the inputs of one of the bidders. This is something people have been doing in adversarial machine learning to try to defeat classifiers. And it's got this kind of analogous flavor here. Here it's trying to defeat the incentive alignment of the mechanism. So I actually have a little animation here so you can see how this goes. This will repeat and you'll be able to watch it a few times. This is showing that gradient ascent dynamics for a well-trained neural network. Again, you can think about this as a single bidder, two-item neural network. The green dot here is the true valuation of the bidder. And what we do is we randomly initialize at these red crosses, we randomly initialize the gradient ascent process to try to find regret improving misreports. And you can see that because this network is well trained, the gradients of these misreports find their way to the truthful report. And so that's because this mechanism has already done a good job of aligning incentives. But if it had not done a good job of aligning incentives, the idea would be that some of these paths would end up away from the green points, and then we'd be able to check to see whether the utility is better than the utility when you truthfully report. Is there a question?
Yes, so let me see if I can read the question. So the question is with regard to RegNet. The payment part of the network outputs a single A sub I per bidder. The fraction of her declared value that she will pay for the bundle she won, regardless of that bundle. Isn't the fact that that fraction is independent of the bundle that the bidder actually won restricting for the network?
No, because we train the entire network at the same time. And so if we were to train these separately, I could see why there might be tie-breaking issues. but because we train it at the same time, it's not restrictive. Okay. So let me now go through the same exercise I went through with RocheNet, with RegretNet. And remember that we don't give RegretNet the same type of economic theory that we give RocheNet. We don't tell it that picking something from a choice set that's independent of your reports will be dominant strategy. So it's not clear that this regret penalty will successfully align incentives. And here are the density plots we get from RocheNet. They're not as crisp because it's not working with this maximization over hyperplanes in the same way that RocheNet is. But you can see that it's learned the essence of the optimal auction design. And I can show you also that for, I don't have another picture, but I could show you more pictures of this, and the density plots would continue to do a very nice job of matching the boundaries from optimal designs from auction theory. Because this is RegretNet, we can now do multiple bidder problems. And so we can take the Minnelli-Vincent setting, and we can take it to 2 bidders rather than 1 bidder. And we need some baselines here. In this case, the baselines that we compare to are baselines from the computational automated mechanism design literature that you can think about as essentially searching through a affine weighted maximization, kind of VCG-like family. And you can see that as we train, the revenue is able to surpass those baselines. You can also see that as we train, the regret is quickly driven down to zero, to very close to 0. Here's another example of this. This is a generalization of a theoretical result due to Yao from 2017. Again, for a 2-bidder, 2-item setting, we've picked it because it's a simple generalization of something in the literature that provides analytical results. And here you can see that again, as we train, the revenue that comes from RegretNet is able to surpass the 2 baselines that we compare to. And here we compare to the optimal item-wise Meyerson auction and the optimal bundle-wise Meyerson auction. And you can see that the regret again reduces during training, and you can see that the effect of the regret reducing during training is to drive the revenue down. Initially, this is a relaxation, and we're achieving more revenue than we should. And then as the mechanism becomes strategy proof or approximately strategy proof, the regret falls but remains above the baselines. The last thing I want to show you with RegretNet is to a larger setting. This is a setting with either 3 bidders or 5 bidders and 10 items. Again, it's additive, uniform 0-1 values. We know from Palfrey 83 that item-wise Meyerson is optimal in the limit of a very large number of agents in this problem. And so from that perspective, item-wise Meyerson is a reasonable baseline. But again, we don't have optimal analytical results to compare to. What I want to say here is that the revenue from RegretNet is higher than those of the baselines, and that again, the test regret is very low. Here we use a larger network. We use a network with 5 hidden layers, each with 100 units in each layer. You might be wondering, well, how long do these networks take to train? This network took around 12 hours to train. You might be wondering, well, that seems like quite a lot of computation. Well, yes, but a linear program with a discretized representation of this continuous type space would take more than 1 week, even on a 2-bit 3-item version of this problem. So it is true that these compute times are non-trivial, but we don't know of a better way to attack these problems at the moment than the techniques that I'm sharing with you. I want to also share some theoretical observations. First of all, we do prove some generalization bounds. I'm not going to share that theory with you, but this essentially says that the empirical revenue or the empirical average ex post regret you get for a given function in the function class will generalize with high probability to the actual distribution with only a small error. We show in an extended version of our 2019 paper that it looks like techniques like RocheNet can be used to also develop new theoretical results. So we used RocheNet with a single-bit triangle distribution, which I'm not going to explain to you in detail. And by testing it on different settings of that distribution, and by visualizing the optimal rules that were generated by RocheNet, we were able to guess an analytical form, and then we were able to use the duality theory to be able to prove the optimality. And then we've also used this to support conjectures in the literature. There's a conjecture by Giannakopoulos and Koutsoupias. They conjecture the straitjacket auction in their language, which is a generalization of the Manelli-Vincent setting to multiple items. So they prove its optimality for 1 through 6 items, and they conjecture its optimality for 7 and more items. And we're not able to affirmatively confirm the theorem with these approaches, but we're able to generate revenue that is very suggestive of the optimality of SJA. Okay, so that was part 1. This will be a good time if you have any lingering questions about this idea of using a differentiable representation of a auction mechanism. This will be a good time to ask before we talk about matching. Yeah, Martin.
So this is super fascinating. I'm just wondering, what are the limits of the technique when it comes to auction design or finding optimal auctions? And in those environments where we don't know the analytical solution, how can I be sure that this is indeed the optimal solution that I found, the optimal mechanism?
Right. Yeah, that's a great question, Martin. So a number of limits. We don't know how to scale these approaches yet to combinatorial problems. And you can imagine that you can use the same succinct representations that we're familiar with at the input, but you still, and I think this is more challenging, need to find the right succinct representations of the distributions over allocations at the output. So we have shown results for 2-item combinatorial problems, but we haven't shown results for more than 2 items. So I think one very exciting frontier is to use these techniques for combinatorial auction problems with multiple items. And then on your second question, it's a huge open problem to find good upper bounds from suitable relaxations of these very difficult optimal design problems. The duality theory that we used here, due to Daskalakis et al., is quite rare and applies to a single beta setting, not to a multiple beta setting. And so one of the big gaps in terms of theory that is a limitation for what we can do with our techniques at the moment is precisely that it's challenging for us to be able to argue that we've found the provably optimal outcome. Because under the hood here, of course, we're solving non-convex optimization problems using SGD. We're doing what people in machine learning are doing with pretty good success. And we're also getting pretty good success, but with limited theoretical support that would suggest that you would expect to optimally solve these problems. And I think we're showing promising results, but I think this is the start of an agenda.
Excellent, thank you.
Yeah. Okay, let me talk about matching. This is the second vignette that I wanted to give you. I think this audience is very familiar with matching problems as well. So let me situate this quickly. Imagine that I have a two-sided matching problem with workers and firms. Suppose that each side of the market has strict preferences over the other side of the market. For example, worker 1 has this preference order. I most prefer firm 2, then firm 1, then firm 3. Firm 1 most prefers worker 1, then worker 3, then worker 2. Matching is a one-to-one mapping between workers and firms. In general, we allow agents to be unmatched as well. And in general, we allow agents to have truncated preferences, such that they prefer to be unmatched than matched with anybody on the other side of the market. A crucial notion in two-sided matching is the notion of stability. This matching is unstable. Why? Because there's a blocking pair. Worker 1 prefers firm 2 to firm 1, and firm 2 prefers worker 1 to worker 2. So say worker 1, firm 2, block the matching. This is an unstable matching. In comparison, this is a stable matching. There are no blocking pairs. So what we've been doing in ongoing work, this is work with Zhe Feng and Sai Srivatsa Ravindranath, is we've been asking whether we can use the same differentiable economics approach to try to understand trade-offs between stability and strategy proofness. Of course, there's a theorem, Al-Raf 82, that shows that there is no mechanism that is both stable and strategy proof. And of course, we have Gale-Shapley deferred acceptance, which is stable, but only strategy proof on one side. If you wanted full strategy proofness, you could use random serial dictatorship, where you ask a randomly selected, currently unmatched agent to point to the agent on the other side that it most prefers. As you can see, this would be horribly unstable, but it would be strategy proof. And I hope people can write to me after this talk, if you're out there in the audience. As far as I know, there's not very much known about how to make trade-offs. We have an impossibility result. We have point solutions in the matching literature, and we don't know very much else, as far as I know. Please write to me with literature that I should know about. So the question we're asking is, can we identify new trade-offs between stability and strategy proofness? Not going to have time to walk you through all of the detail of this network, but it's not as complicated as it looks. The input now is a cardinal representation of the ordinal preferences of each agent. So this might be the input part that's representing the preferences of each of the workers, and then these nodes represent the preferences of each of the firms. I now have a multi-layer neural network here with 4 hidden layers. They flow into what's called a soft plus unit, which is just giving me a non-negative value. I've got kind of n times m of these. I've got two sets of them. I mask those non-negative values with a Boolean mask that will ensure that I get individual rationality. it will prevent a worker being matched with a firm with whom she says she is not interested in being matched with. I then have what you can think about as some machinery to generate eventually a doubly stochastic allocation matrix. And it's that doubly stochastic allocation matrix that I need and that I can use through the Birkhoff von Neumann decomposition theorem to get a distribution over integral matchings. And we have to do some normalizations to get there. We take some mins. You can probably imagine how that goes. Crucial thing is that this whole network is a differentiable representation of a mapping from a cardinal representation of inputs to a representation of a doubly stochastic matrix. This R matrix itself may not quite be doubly stochastic. We do a little bit of additional processing after this. So what are we doing? We're working with randomized mechanisms. When you have randomized matching mechanisms, you need to replace stability with this concept of no justified envy. It's really the same idea. No justified envy says that no pair prefers each other to their fractionally matched partners. And then what we do is we define a differentiable quantity which measures the expected stability violation. Strategy proofness becomes no gain in utility through a misreport. It's actually expected utility because we have a randomized matching rule. But it's still ex post with regard to the reports of everybody else. And again, we define a quantity which is differentiable once we have these defeating reports that looks a lot like the expected ex post regret quantity from the auction setting. This, again, would reduce to strategy proofness for deterministic mechanisms. Those of you that are very familiar with this literature will be wondering, why am I talking about a particular utility function? There's a stronger notion of ordinal strategy proofness that we can also work with, but I'm not showing you in these results. Once we set this all up, we have a loss function that is making a trade-off. When lambda is big, it says I care about stability. When lambda gets closer to 0, it says I care about strategy proofness. What do we do? In the simulation result that I will show you, we sample uniform preference orders for each agent over the other side of the market. With some probability, we truncate that preference order. And we also allow for correlated preferences. So we allow for there to be these particular starred preferences, which with some probability you adopt rather than your independently sampled preferences. And we compare the learned mechanisms with deferred acceptance and RSD, and these results are for a 4x4 market. And I'm showing you here the frontier of trade-offs that the network is able to learn as we vary lambda between a larger lambda that cares about stability and therefore has almost no stability violation, and a smaller lambda that begins to care, or a smaller lambda that begins to care more about strategy proofness and has almost no strategy proofness violation. And what you can see, we've added RSD and deferred acceptance to the plot. And you can think about the convex combination of those mechanisms. What you can immediately see visually is it looks like there are some interesting targets for economic theory. It looks like there are a number of mechanisms that are considerably more strategy proof in the sense that I've defined it here than deferred acceptance and are almost as stable. And it looks like there are mechanisms that are considerably more stable than RSD and almost as strategy proof. And you might ask, well, what do these mechanisms look like? And you can ask, for example, how similar are these mechanisms to deferred acceptance? So this is a plot showing you that as you increase lambda, remember higher lambda, I care more about strategy proofness, less about stability. So, opposite, higher lambda, more about stability. So you'd expect as you go to the right, these mechanisms that we're learning for different distributions on preferences would become more and more similar to deferred acceptance. The region I was showing you that was interesting was between around 0.1 and 0.05. So there are a number of mechanisms that are being generated that are quite different from deferred acceptance, but still appear to be very stable, and they look to be more incentive aligned than deferred acceptance. And so it seems to me that there's some interesting opportunities here to try to do some new economic theory in this space. And you can also, by the way, look to see whether these mechanisms are deterministic or randomized. And these interesting mechanisms seem to be randomized. Okay. So I know I'm running toward the end of my time. I want to make two quick comments before we wrap. One is that all of this was about direct mechanism design, but these problems, taxation, congestion pricing, contract design, are indirect. They're about designs that induce a game that is played by the participants. They're not about designing functions from inputs to outputs. What can we do in this case? We cannot impose incentive compatibility. I'm going to skip this example. The new challenge here is that you have to model the equilibrium behavior of agents. We want to point out here that it becomes a two-level learning problem. You're learning the rules of the mechanism, while the agents at the same time are learning how to play the mechanism. And we've been doing quite a lot of work on this recently, which I'm not going to have time to share with you in any detail, but I will advertise. So we have a paper in AAAI 21. This is work with Gianluca Brero, Alon Eden, Matthias Gersgrasser, and Duncan Rangens-Yu. This paper shows that you can use reinforcement learning for the design of a particular class of indirect mechanisms. I'm going to skip the details. We use a partially observable Markov decision process formulation. And then the second advert I would like to make is that we introduce a little bit of communication into the mechanism as well. So now you have the opportunity for the agents to not only take actions within the economic environment, but to send messages. And this introduces a game, and in a working paper with Gianluca, Alon, Matthias, and Vincent Lee, we have work where we're using multiplicative weights to learn the play of the agents and reinforcement learning to learn the design of the mechanism. And we're looking to see what happens when we do those two things at the same time. We're going to have to skip those two results. I want to wrap with the following points. Martin already asked me about the challenges. I've kind of shown you what we can do. I haven't talked very much about what we cannot do. It would be nice to have ways to have a single network that can generalize to different numbers of agents and items. Right now, we generally train one network for different economic contexts. There is some work by Rama et al. From Princeton, which appeared in AAAI 21 on doing something like that. We'd like to continue to find ways to leverage characterization results. For example, bringing monotonicity or agent independence into the architectures of the neural networks. We'd like to have ways to transform approximately incentive compatible mechanisms into exactly incentive compatible mechanisms. My student Zhefeng with his collaborators has a way to take a approximate strategy proof mechanism a la RegretNet and convert it to an exactly Bayesian incentive compatible mechanism for the case of uniform type distributions. We'd like robustness. Might incentives be bad on the parts of the distribution that were not sampled enough during training? John Dickerson and his group at the University of Maryland have been working on generating ways to certify the regret of the rules that are trained. And then lastly, as I said, we'd like indirect mechanisms. This gets into topics like Stackelberg learning, two-level multi-agent reinforcement learning. I have worked with my collaborators at Salesforce AI on tax policy and what we call the AI economist. And then we have a large multi-year project at Harvard I'm dying to share with people about Atari Economics, which relates to this. And last point, we'd like interpretability so that people can understand what's been learned. And bringing in behavioral considerations. So just to conclude, this is a new use of deep neural networks for end-to-end economic design. It's a data-driven approach, seems to be able to attack problems currently out of reach of economic theory. It's all about using in-expectation objectives, and it seems to be very flexible. We're calling this differentiable economics, and there are a few papers here that you can read if you'd like to learn more about the work. With that, thank you, and apologies I went slightly over.
Thank you so much, David, for this excellent talk. There's one question in Q&A, and we can also open it up for discussion for a few minutes. So I read that question. Clayton is asking, this is about the two-sided matching network. The question is that network related to the possibly well-known representation of the set of stable matchings as a linear program? So this is a result, yeah.
Yeah, no, it's a great question. The answer is no. We have used that polytope in other machine learning work. So I have a paper from 2018, I believe, with Hari Krishna and Narasimham, where we do use that polytope, and we train you can think about it as training a scoring function that picks particular extremal points on that polytope as are appropriate to the design problem. The thing that I want to point out is that is a very nice, succinct linear program that represents the set of stable matchings for a particular input. That polytope cannot be used for the mechanism design problem. The mechanism design problem has to map every possible profile, every possible input into a matching. And so that polytope is not immediately applicable, but I think it's a great example of, well, could we find a way to bring that geometry, that understanding, that type of characterization into the work? We haven't done that in this work yet, but I think it's an interesting direction.
All right, great, thanks. There's one more question, which is kind of a broad question. And asks, can you tell us a little bit about Atari Economics?
Thank you, Amy. Thank you for asking. Yes, I can tell you a little bit about Atari Economics. We are working on a multi-agent Atari framework, which we are also augmenting with resource constraints and economic mechanisms. So you probably know that over the past few years, some progress was made in deep reinforcement learning in the mid-2010s, around 2015, 2016 by DeepMind, where they innovated deep Q networks to play Atari games. So Atari games are kind of interesting because there are a whole bunch of them. They're fun for humans to play. They are kind of just interesting enough to be not easy for AI systems to solve. And what we are doing is we're doing things like taking Space Invaders and actually making you have to bid for bullets to fire at aliens in the Space Invaders game. And then using multi-agent reinforcement learning to understand how agents in these very resource-constrained, very dynamic environments would respond to different, simple, indirect mechanism designs. So we're actually using a multiplayer Atari framework that we're developing to provide ways to study automated indirect mechanism design. And we're also doing this with human data coming into the system by using crowdsourcing, because people love to play Atari games. And so we're also bringing in human behavior into the design loop. Don't have anything to share with you written on this yet, but we've been working really hard for multiple years.
Great, thank you so much, David. So if there is no other question, thank you everyone for attending. And again, thank you, David. We very much enjoyed this really insightful talk.
Thank you for the opportunity.
Thanks so much, David.
Thank you.
Bye.
Bye.
It was fun.